Having me. Hi, everyone. Just to quickly check, you can see my mouse cursor, right?
Yep.
Yeah, okay, that's great. Yeah, thanks for the introduction. I'm Michael, and today I would like to tell you more about our recent paper about how to do molecular dynamics with diffusion models. Actually, it's a bit more than that. Actually, we aim to have a diffusion model that can do both sampling and simulation. And for this, we use an energy-based parameterization. But more to that in a minute. So I guess you are all experts on the topic, so I don't really have to explain a lot of theory and background. But just to get everyone on the same page, so the underlying principles here are obviously molecular dynamics. And here we have a simple molecule, alanine dipeptide, and the molecule tries to avoid to staying in high energy states, defined by some potential energy function U here. And when we want to simulate, we follow the negative gradient of this U. And this whole thing are the forces that guide how the molecule or how a biochemical system evolves over time. And we can use multiple different ways to simulate such molecules. A very common way for this is just Langevin simulation, where we have this stochastic differential equation and where we just use basically the forces, some friction, and then some Gaussian noise in each step. The important property of this we will need in this presentation is once this integrator, but we don't need that, like just you should know that this exists, and the Boltzmann distribution. So if we let this MD simulation run until it has converged, the samples of the molecule will be distributed according to this distribution, the Boltzmann distribution, and it is defined by the potential energy. Basically, it's just a negative exponential. Plus here, if we want to actually define a density, some normalization constant. And what we are interested here is to do molecular dynamics in some way or another. So here you can see for the same molecule as for in the previous slide, how an MD simulation looks like. So this is a protection into 2D space. And MD simulation is great because it gives us a principled way to explore a system and also give us kinetic properties. However, the drawback is like it's very sequential and very slow. And we can't really like do any coarse graining with MD simulation directly because like to define the forces, we need to have like knowledge about all atoms and how they interact with each other. On the other hand, for a lot of properties, it is sufficient to just look at the Boltzmann distribution. So when we run this MD for infinitely long until it converged, what probability does each individual state have? And this is nice if we can draw samples from this distribution, but it doesn't give us any kinetic properties. Like for instance, when we want to see how it goes from this state to this state, we can't really do this or need to draw a lot of samples. Um, there are diffusion models that work on both sides. So for instance, here, diffMD, a diffusion model that does MD by taking one sample and trying to predict the next sample with diffusion, or here also an energy-based way on how we can sample from the Boltzmann distribution. But in this work, we want to propose a model that can do both. So do sampling from the Boltzmann distribution, the classical diffusion sampling, but also being able to use it for sequential simulation. And having such a model opens a lot of possibilities because we can quickly explore our landscape and also can use like decades of research that make use of forces and potential function like umbrella sampling and some other enhanced sampling techniques. Yeah, I guess you're also all pretty familiar with diffusion and probably have seen this figure hundreds of times. I stole it from the Song et al. Paper, the score-based diffusion process. But I think it nicely explains how we can go from a sample to noise, like in this diffusion process where I have the SDE and then apply some noise in each step until eventually we converge to Gaussian noise. And in the end, what we're trying to learn is a denoising function that can then start from the noise and then iteratively denoise it until eventually we reach the sample again. And for this, we need the score function. But let's first look here at a simple example. So for instance, here we have just a two-dimensional Gaussian mixture distribution, and we start from a single Gaussian, and then what happens in diffusion, like it splits it apart. to generate samples from these modes. And here it's important, like we need to apply the model a lot of times sequentially to converge to a distribution. And under every diffusion model underlying, there is an SDE, a stochastic differential equation. And here it's very simple, like how we have an f and a g, that's hyperparameter function basically, and determines how the stochastic process happens, and basically tells us how we can corrupt our samples to noise. So this W here is a Wiener process, some Gaussian noise. In the simplest form, we just take our initial sample and add a lot of noise until the sample is not recognizable anymore. And the nice thing about this SDE is that it has this reverse version with the score function I was just telling you about. And the score function is basically the marginal density. So it's the log PTX. So basically it describes at time t, what's the probability of being in state x, and then the gradient of it. So basically it points towards these high density regions. Um, yeah, and the goal is to learn the score function. And for this, we can use denoising score matching principles. And what we do is we just assume that we want to learn this function and use a neural network typically to model this function directly. So this S theta is basically our neural network. And then we have some target score we are trying to match. I think this is well known for a lot of you, but this is the part where it might be interesting or at least novel to a few people. So the idea is now how can we use a diffusion model to simulate? And for this, we need to make one simple but crucial assumption, namely that our underlying training distribution is distributed according to a Gaussian. So the same Gaussian we saw before. So here exponential negative u and some normalizing constant. And if this is the case, we can draw a simple relation that's actually very insightful. So here on the left-hand side, we again have our score function. And if we evaluate it at t0, what we learn is basically just the definition. Like if our training objective is met, what we learn is the score. So we learn the gradient of log p0. But in this case, our p0 is this Gaussian. Is this Boltzmann distribution. So what we can do is we can just plug it inside and then make some simplifications. So here, just using the Boltzmann distribution, this log and the exp cancels. The gradient here of a constant vanishes, and all that remains is the gradient or the negative gradient of our potential and some temperature-dependent term. And this reveals a very interesting property. So this means the score at time t0 is actually the forces that act on molecular systems. And this means if we have Boltzmann distributed training data, what we can do is we can just train a diffusion model the way we always do. So just taking samples, and then we can extract the scores or the forces out of the score by just a single model evaluation. And also, I think this gives some nice intuition about the diffusion sampling process. So when we think about this process, we start from some noise, and then step by step, we go closer to the samples. And what happens as we get closer and closer to zero, the score kind of becomes more physical until eventually it's actual forces. And in the end, it's just doing basically a few steps of MD simulation or something very similar to MD simulation. Okay, now this gives us two different ways with such an energy-based model to access like the probability, like from what we actually learned. One, we have this denoising score matching, the classical diffusion process, which gives us of this P of X. And then we have another way of evaluating this probability. So basically defined by the score and this relation, we can also define again with the Boltzmann distribution what our probability at time t0 should be. And basically for a well-trained diffusion model, this should be equivalent. And if we can actually manage to find such a model where this is equivalent, this is really nice. Let's look if diffusion models actually fulfill this property. So we have again the same target density we used before. So a mixture of two Gaussians, one weighted with 20%, the other with 80%. And Yeah, okay. The normal IID sampling process works. I showed you this animation earlier, and this is not really surprising because diffusion models, we've worked with them for years now. They work well. But the more interesting thing is, can we actually extract this score potential, the score density relation from earlier? Uh, and the unfortunate news is that no. So here, even for this simple toy example, when we use the score, learned score uh, to extract the energy out of it at t0, we see that this is not consistent with the target, with the reference, and also not self-consistent with the model. So it basically learns two different things. And interestingly, here we see that once it doesn't learn the weight between the two modes correctly. So here it's not 20%. And secondly, we have this weird mode in the middle. And this is because when we do this diffusion process sampling, what happens is that like here, after let's say 50% of the time, the two modes are already split. And from that on, the neural network doesn't really care anymore on how it needs to split and distribute the densities anymore. And all the training data will just be here in the corners because it just takes noisy samples from here. But as the time goes to zero, the noise will become very small. So this means actually here there's almost no training data, which makes the problem harder. Um, and this can also be seen in the loss. So if we look at a trained diffusion model here over diffusion time, so this is not like loss over training, but a trained model evaluated at different diffusion times. When at 1, we have our noisy distribution, and at 0, we have our data distribution. We see that it's very easy for the model to learn the noisy process, so the noisy score, which basically just maps one Gaussian to another Gaussian. And on the other side, we have our data, and here our loss is the largest. So basically, it's really tough for the model to learn the loss at small t. But that's unfortunate because this is the area that we actually want to score and need it to be evaluated. And intuitively, this has a simple like this can be explained very intuitively because all like if you just map some Gaussians to Gaussians, it's simple. But if you have almost a molecule, almost a picture, and then need to maintain the structural fidelity, it's really hard to not destroy anything. So it's just plain simply a harder task. But also, unfortunately, we have some numerical instabilities. So for instance, when we look at the training objective from before, usually we rephrase it like this. So we take our score, our neural network, and then apply it to some noisy samples, and then match it with the target noise. And what's happening is that here, this is epsilon, so a random Gaussianly distributed variable, divided by our noise. And this noise level is dependent on t. And as t goes to 0, this vanishes and goes to 0. So this means the loss here is going to explode because we try to divide something 0 or something very close to 0. This is not really an issue for normal diffusion training because all we do is just we take a small epsilon and then just don't train until 0, but a small epsilon. But here in this case, like it makes it tricky because this is the area we're interested. Also, you could try to rephrase this by multiplying the whole thing with sigma t. But what's happening then is that this neural network is multiplied by a small number, and then the network output needs to be really large, making again the whole training unstable. So yeah, this is just an inherent problem of diffusion models, making the training maybe a bit harder, and the problem in general a bit more difficult. Yeah, the question now being, how can we actually solve this problem? How can we train a diffusion model that's self-consistent so that we can use it with classical diffusion sampling and also sample the density like with one step. And as I said before, this is really nice because this gives access to uh, generating independent samples just with diffusion, or here sampling with simulation, or also extracting the energy out of it in a meaningful way. And doing all of this, just taking training samples and don't having access to any forces or anything else. For this, in this paper, we make use of the Fokker-Planck equation. And the idea is somehow that we want to make the whole model consistent over time. So basically, as the density changes over time, we actually want to take this consistency and have it in every at every time t. And the Fokker-Planck equation is basically what describes this consistency in some way or another. So this is the Fokker-Planck equation in the log form, framed for the stochastic differential equation of the diffusion model we already have. So basically here on the left-hand side, we have our partial t log ptx, so how our density changes over time. And on the right-hand side, we have to score a few times. So this is what we learn. And basically what this equation puts into relation is if our model predicts some score, let's say in this step, like shift those two modes apart, then in the next step, the density also has to increase at this point. So what the score predicts should also impact how the energy changes, how the slope PT changes, how the partial, like how it changes over time. And this is not something that's like new or anything in general. And any well-trained diffusion model should fulfill this equation. However, it's not really needed in practice because we do this score matching objective, which doesn't need this equation. But does a well-trained diffusion model actually fulfill this equation? And the answer is unfortunately no. And if we look at this Fokker-Planck error, so the deviation from this Fokker-Planck equation over diffusion time. So again, here we have our noise and here we have our data. We see that for the most part, it's like low or a constant. But as we get close to zero, this Fokker-Planck error peaks and like basically explodes. And we see this is in log plot. There's a log plot. So here, this is in log scale, which means that like it gets really large, like almost 2 orders of magnitudes increase in this deviation. Okay, now this is fishy. So let's try to fix this. And we propose to enforce this Fokker-Planck equation with an additional regularization term during training. So the idea is simple. If it doesn't fulfill this equation, let's just use a simple loss that evaluates this equation and just say, all right, the left-hand side, subtract the right-hand side from it, and then just use the L2 norm and then minimize it. And we then add it to the usual denoising score matching loss. So this is the normal diffusion training loss. And then we just add this regularization with some regularization strength alpha. Here we have to think about one thing. How do we sample this X and T? With diffusion, we have this noise process, right? So we take noisy samples. Here we could use anything for this regularization. We decided to also stick with the samples from diffusion, although this could also be used like with more noise, for instance, to provide a training signal also where diffusion can't. Because as I said, as we had before, like at T0, so when we have no noise, which basically just have the training samples, no noise. And here we could like enforce some basic noise, add some noise to all the samples and train it for a more flexible model, more generalizable model. Okay, so this is the same figure as before. We saw that with normal denoising score matching, we get a non-consistent model, so not a proper energy-based model. So basically we get two different probability densities, or energies in this case, with one time in sampling works perfect, whereas here we don't really learn to recover the density. Now the question is, does it work with the regularization? And yes, it does. So here we see that diffusion sampling works the same way. And once we introduce this regularization, like we can actually recover the density at T0. And this shows that the Fokker-Planck regularization improves the consistency, at least for this simple toy system. But why is this actually the case? So the idea is that the diffusion process generally is learned well, because otherwise our samples wouldn't look good. So for most of the diffusion process, our learned score is accurate. And now the idea is with this Fokker-Planck regularization that here in this area it's good. So kind of let's push it by linking two t's. So basically we have this condition on the partial t that basically links two neighboring points. And then as we link neighboring points, it will push this consistency forward. And with this Fokker-Planck regularization, obviously the Fokker-Planck error goes down because this is also what we do during regularization. And we see here almost 2 orders of magnitudes smaller with the regularization. And with it, as in the previous slide, we saw this improvement in the density evaluation, the energy evaluation. And here you also see this dip and then this peak. And the reason why it stays rather consistent here is because we use some time-based weighting scheme where we put more emphasis in the loss on this area, because here is the area we actually have a large error and want to improve our sampling. In practice, it's not that straightforward to evaluate the Fokker-Planck equation. So for instance, here on the left-hand side, we have the partial t of log pt. And usually what we learn is just the score. So we learn the score is the gradient of log ptx. So what we have to do instead is an energy-based parameterization to give access to this equation, which means that basically we take the gradient of our neural network. And on the right-hand side, we have this nasty term, which is pretty inefficient to compute, the divergence of gradient of log pt. And since we use an energy-based parameterization, we need to do here gradient, and then this divergence term is the trace of the Jacobian, so another gradient, and then doing optimization, we need to do another gradient. Yeah, so that can be pretty inefficient. In the paper, we introduce a stochastic approximation to do this faster. Still, evaluating this whole loss is increasing the training time by about 7 times. So we need some ways on how we can handle these computational burdens and make training actually feasible. And for this, we do a very simple trick. So we say, okay, the Fokker-Planck error is large in this region. So let's just apply the regularization here. Sounds simple. The problem is that like if we train in batches and sample our diffusion time uniformly, then we will always have an element where we apply the Fokker-Planck regularization, but also batch elements where we don't. And since our batch is determined by the slowest path, we don't really gain any speed up. So we need to apply a trick, and we decided to borrow some ideas from image diffusion models, where they split the diffusion time into multiple independent and disjoint intervals, and then we just use one expert trained on each interval. Okay, so this sounds fancy. Actually, it's just simple. So if we have here our diffusion time, what we do is we just don't train a single model, but say we train a model on this area, on this time, and on this time. And here for this, we can use smaller models because, as I said before, just mapping Gaussians to Gaussians is a simpler task. And we don't need the energy-based parameterization. Whereas here, we need probably a larger neural network. And this is the network we want to apply the regularization to. And interestingly, this gives us a few interesting advantages. So one of which is that we can use more parameters with this. So imagine we have 3 different models and split our time into 3 ranges. What we can do is we can max out our GPU memory for each model. So basically, we can use 3 times the number of parameters. Also, it's usually easier for the models to train on because it has a very, very narrow range on what it is trained. So instead of training one model on the whole diffusion range for needing to understand Gaussians and also very detailed molecules, we just say, okay, this is your narrow range, and it's easier for the model like to overfit and be very robust on this range. And also interestingly, we did some experiments, and these performance benefits go beyond scaling. So although we use more parameters, it is better to use mixture, like allocate these parameters more efficiently and get better results than just using a larger model with this mixture. And the idea again is because we have just know how we can distribute our performance mostly to this diffusion time. Yeah, and a neat benefit is if you're just interested in the forces or the potential, you can just not train these models and just train one model on a subrange, and this makes it a bit stable. Okay, so let's look at some results. How does the mesh method actually, how good is the method actually? And here are some results for the small system adenine dipeptide and also for proteins. And I know this is now a big figure. Stay with me for 1 second. It's not too complicated, I swear. So here on the left, what we see is the reference, so the target free energy surfaces that we want to achieve is for alanine dipeptide, for chignolin, and for BBA. And then we have two blocks, so here and here. And here we compare standard diffusion models, like existing models, and then our approaches. And then here we have on the left and on the right two ways on how we can generate the samples. So one with the diffusion sampling, the generative process we all know, going from noise to Gaussians. And then here we can use the simulation. So we use this relation to extract, to take the network, evaluate the T0 and then or small t, and then extract the forces and then do a long running MD simulation. And basically those two should always match. So here those two should match and those two should match. And we can see that IID sampling here works for all systems very well. So here, let's say diffusion sampling works well. It looks like the reference here for Chignolin, for BBA, also for our method. Like, yeah, diffusion works. So this is common. The new part we do is here and here. So this is 2-for-1, another paper that tried to use this relation to actually recover this, but they didn't do any tricks. So they just basically trained a diffusion model and then evaluated the score. And what we can see is that if you don't do this Fokker-Planck regularization, you get inconsistencies. So like we saw in the 2D case, your IID sampling performance looks different from your simulation. Here we see it's washed out, and for BBA, like it separates into these individual modes, like it doesn't really fold properly anymore. It doesn't really seem that usable anymore. Whereas for small systems, like here it works, kind of works, and as the system size increases, it becomes worse and worse. Here for our system, we can do both. So we can sample and simulate and match. And we don't have these issues, showing that the Fokker-Planck regularization kind of improves the stability at small t. Okay, so this is now just alanine dipeptide from the previous slide with one more plot. So basically we have here now IID sampling and here again the simulation. And here we see a small difference. So what happens when you train a diffusion model for simulation and use T0 as evaluation is actually this plot on the left. So what happens is that you don't find this mode. And this is because, similarly as in the 2D sample, like the weights between the modes is not learned properly. So the energy barrier is probably much higher than before. So like it just can't transition to these modes. And 2-for-1 proposed, okay, if T0 is unstable, why not use larger T, let's say 0.1. And we see here that it seems to solve some problems. Like we can find this right mode, we can cross this high energy barrier. But unfortunately, since we now use a larger T, we use a score that was trained on the noisy target. So if we now look at some observables, like here the bond length between carbon and nitrogen, what happens is that all models nicely learn, or at least closely resemble, the target reference here in black. However, 2-for-1 learns a noisy version of all these metrics because it was trained on noisy samples, so it will only recover noisy structures. So although the Ramachandran plot here looks nice and seems to give some intuition, Actually, it's not that useful, I would say, if you need high precision for yeah. Yeah, and the really nice thing now is that we can do both with diffusion models. So not just do independent samples from molecule to sample from the Boltzmann distribution, but since we can extract forces, we can do simulation, giving us access to kinetic properties. So here you can see a single trajectory like simulated with our model of BBA and how it changes over time. And here you can also see a simple analysis on how like some still frames, how it goes from some unfolded state here in the tick space to another space and then to the two different folded representations. And this is something you couldn't really do without this dynamics because just independent samples don't really give you any notion on these kinetic properties. And this is great because with this model, you can do a lot more analysis and hopefully will be useful for practitioners. And yeah, you can also do some other analysis of the kinetics. Maybe some of you know more about this. I'm a computer scientist, so I don't really know what the best way is to analyze such systems. We did a simple analysis by taking the tick space and then separating it into individual states, and then just looking at the Markov chain probabilities going from one state to another and comparing it with the reference distribution. I'm sure there are cooler and more interesting things you can do with these kinetic properties. Okay, now there's the question, can it actually make sense to use this model just for dynamics? As before, I was saying, okay, we can only train this small model on the small diffusion times and only use it for kinetics if we're not interested. So we also benchmarked against force matching approach that also do coarse graining, but instead of our method, which just takes samples from the equilibrium distribution, they use forces and then use the force matching objective to train the model. And we can see that our Fokker-Planck regularization and our diffusion model actually consistently outperforms these methods, showing that just taking samples, no priors, just a simple neural network can outperform even force matching. So when we have less data, which is really nice. We also did some transferability. So we took the data set from Time Warp, which contains basically all possible combination of the 20 amino acids and built dipeptides out of it. So 400 dipeptides with 49,000 samples each. And out of those, we have used 175 dipeptides for training and then evaluated on 50 dipeptides. And what we can see here is very similar trends to before. So again, it's 2 for 1 with this noisy, like with this larger T, produces washed out noisy distributions, but still generally resembles the reference distribution rather well. However, once we actually want to have this consistency, we need this Fokker-Planck regularization. And also here we have a separation, how much difference, ablation study, how much we had from this mixture of experts. So here we see a comparison between just taking diffusion simulation and then also the mixture simulation. So basically the difference between those two is just training one model on the whole range or just training one model on a sub-range. And we see, especially for this transferability, we found that it generalizes much better and is more robust. And this again makes sense because now it just sees some very similar samples and it already has to generalize across systems. And now at least it doesn't have to generalize across a huge noise level range. Yeah, and if we look at some numerical results again, like before on this potential mean force error and the Jensen-Shannon divergence of samples, what we are mostly looking for in our models is one, that the model produces good results, that are close to the reference distribution, and two, that those two formulations agree. And we see here with this Fokker-Planck regularization and in combination with mixtures, especially, we see that here, for instance, IIT performance and simulation performance matches almost perfectly, like also here with this PMF area, which is a bit of a better metric for molecules and just the Shannon divergence. And also more interestingly here, we see again now quantitatively that mixture improves the simulation by quite a lot compared to regular diffusion. So here up to 5 times. And this is interesting because mixture uses more parameters because we have a bit more models, but effectively we use the same memory or the same constraint, but the same memory limits, and can do faster training and inference because we just need to apply the regularization to subparts, or we can use smaller models for the large noise diffusion time steps. Yeah, I think the main drawback of this whole thing is that even with our approximation, we need to do compute the score forward 4 times in our training. And we have a very simple architecture. So we use right now a fully connected graph transformer, which scales quadratically, which means that for BBA, for instance, it took 7 days to train on 4 A100s. So future work could definitely include using some better architecture. So not something fully connected if you want to scale it to larger systems. And maybe also include some better approximations. Maybe we could include some stop gradient in the divergence term. Or yeah, maybe we have some other ideas we could do. Yeah, so to summarize, we now saw that we can use any diffusion model that was trained on the Boltzmann distribution and extract an energy out of it, and use this with this score force relation to extract forces out of it. So that means we can use diffusion model trained on Boltzmann distributed data also for simulation. We saw that like there are some inconsistencies during the normal generative sampling process where we just do this denoising and during this sequential simulation. And we propose to fix this by reducing the deviation from the Fokker-Planck equation. What this basically ensures is that the time-dependent diffusion process is more consistent. So we link neighboring, we link scores with similar t's together intuitively. And the interesting thing is that we don't need any priors or force label to get a stable force network. And this is nice because force labels are not always available. So imagine we have some experimental data. We like determine forces. It's not really feasible there. And also a lot of data sets just don't include forces. And yeah, as I said previously, a nice future work would be to reduce computational complexity and expand it to larger systems, maybe also do transferability across these larger systems. Yeah, and to conclude this talk, check out our GitHub. We have some very cool Colab notebooks, which are self-contained. You can just run them and do some MD on toy systems. We implemented this in checks in PyTorch. And also we are right now working on the camera-ready version of our paper from the RIPS, and we'll update our archive very soon. Thank you very much, and I'm happy to answer any questions.
Okay, maybe I will go for the first question. Um, so so can we go back to the Fokker-Planck equation?
Yeah,
So for my understanding is like the regularization is based on the Fokker-Planck equation, which is the log density change.
yeah.
However, the parameterized log density network, or called the energy network, is not actually normalized. So
Mhm.
do you think it would be an issue? Because the whole Fokker-Planck equation, it operates on the normalized density.
Yeah.
If there's a the partition function, if the partition function is included, it would just introduce a time derivative term of the partition functions, and it doesn't fit this equation.
Yeah, so I think in practice, this doesn't really make much of a difference whether we would actually learn the density instead of the energy. On the right-hand side, as far as I can see, all the constants drop out. Here we have the gradient, here we have the gradient. So only here we would have an additional term, as you said. So this would be the partial derivative of the partition function. And I think what implicitly is happening during training, but I didn't test this, but maybe this would be interesting to see, is that since we now also regularize the time partial of the partition function, maybe the energy stays more consistent between diffusion times. Because without this regularization, nothing prevents the model from learning different constant shifts at different diffusion times. But maybe this would also like make this change at least smooth over diffusion time. But in practice, we didn't found any problems with this.
I see. Thank you. And also, I remember in the paper, you used some approximations for the residual loss, which looks similar to the Hutchinson estimator, but I think it's different. Um,
That's
I'm
true. Yes, it's
wondering,
slightly
yeah, how,
different.
how it performs in practice actually. So like, how, yeah, I'm curious about the error when you're approximating it. For example, did you do an experiment and the analytical cases like mixture of Gaussian to see
Yeah.
the error?
So basically, for the toy systems, it didn't make any difference at all which estimator you use, whether you use Hutchinson trace, exact divergence, or our approximator. Um, in For these larger systems, like even for alien dipeptide, it becomes challenging to compute the divergence because for the score to become stable and to be used for forces, the diffusion model needs to be well converged. So you can't really just like train it in full easily. It takes a lot of compute. What we found is that there is a constant shift in the error, basically between analytical divergence and then our estimator. But we didn't find a lot of difference even for ln and dipeptide. So if we train for the same number of epochs, the model looked very similar. Also, I would not claim that our optimizer works better than Hutchinson Trace. I would assume that it performs very similar also in terms of if we look at the loss, like the model, it basically for the model, it doesn't make a difference whether you use Hutchinson Trace or estimator. Um, but we are like, I think 20% faster with our approximation than the Hutchinson trace.
I see. Thank you.
Yeah, sure.
I have one question. A very nice presentation, by the way. So,
Thank you.
any restriction on the training dataset? Does it have to be like a full atomistic system, or it can be also coarse-grained as well?
No, so our systems are all coarse-grained. Actually, the main restriction is just that the data is Boltzmann distributed. Otherwise, this relation doesn't hold. Also, I think it mostly makes sense if you do some coarse graining. Because if you didn't, you could probably just evaluate the forces directly with a force field. And like in all the time that you would spend to generate the training data or if the model, if like right now the model isn't generalizable for larger systems, then yeah, probably it only makes sense with cross graining to gain any
Okay, okay.
real work benefit.
Yeah, then I think it's very nice. Then this the score function you learn is exactly like coarse-grained force field, right?
Yeah, that's really
Okay.
nice. And also there are works like target score matching, which also try to tackle similar problems, not specifically for MD simulation, but to get more accurate scores at small t's. And they use the forces, for instance. So this is something you could do if you have a fully atomistic system. So basically, they use the diffusion loss, and then at zero, they match the forces. But yeah, here with this regularization, we don't really seem to need it.
Okay, cool. Thanks.
Thank
Okay, maybe we will stop here if no more questions. Thank you, Michael, for coming today.
Thank you so much for having me.
Yep. Yep. Okay, thank you very much and see you guys.
Bye.